Hi everybody, this is Time Travel Beard, and in this episode of How to Make Shaders, we are going to go over voxelizing, which is a technique for capturing 3D data about the world so that you can access it to do all kinds of special effects like path tracing or colored black lights with a flood fill, or like anything else you want to do that requires knowing data about the world and not just the pixel that you are rendering. Because Minecraft doesn't give you that data, so you've got to kind of capture it yourself. I'm going to go over the code, and this tutorial is just only doing this, so it's easy to browse through. And it's got a little bit of a help thing here. There's a README file I'll go over, and we'll go over some of these things because they kind of cover how to learn what the code is doing. Like you could see different things. Like we could change how big of an area we're voxelizing. If we shrink this down, you can see the border. Everything outside is red. The default of what we're visualizing is the average color of that face or that block. If we go to 1, we just pick one. What is it? The position. So this is showing us the position of those voxels. Make that area bigger again. Number 2 is 1 pixel's color out of the texture, so this gives us a little bit more variation. Number 3 is light emission. This shows us light sources, and it looks like it has problems with entities. When we switch over the we're to voxelize here, by default we're doing this in the shadow pass, which captures everything. We can also do it just in gbuffer's terrain, which captures just terrain, but probably doesn't capture stuff off screen. But if you were doing this, you probably want to do it in the shadow pass and just only do it for certain things. The way I'm just doing it for everything, it's probably trying to capture data that doesn't exist for those entities, which is probably why it's showing them as emitting light. So you would just not do that for them. And on number 4, we are checking the block ID. We're rendering green if it's grass. We're rendering red if it's grass that isn't surrounded by grass around it. So it's like an edge. I used this for Icarus in my 3D grass shader so that I could have grass be tall where it's not touching other things, and be short where it's a border. So that's one way you could use voxelized data. I also in Icarus use the average color of the face like this in the lighting simulation and reflections that are off screen, because it gives you, like, this is what it looks like off screen. You can also save texture data in there if you wanted to. You could do whatever you want, and you could do whatever you want with it. So let's look at the actual code. This kind of tells you what's where in the README. So we can see that we've got the shader.properties. We'll go over that first. In shader.properties, we're using custom images because we're using 3D images to save the data. You don't have to do that, but it's easier. We have where we're setting a voxel area of how much space to voxelize. We cannot use these sorts of macro defines in this statement. So instead we do the preprocessor directive per each size, and inside of it we set the size of the 3D image. Smaller ones will take less VRAM. That's pretty much all there is to that. We're setting separate AO to true because we don't want to use the ambient occlusion that's included in the polygons, the face's color. Since we're just sampling one corner, we don't want to sample a dark corner versus a bright corner. We want that to just be steady, so we're separating this out. We're setting shadow culling to reverse, and that means that even when things are not visible, they'll still render in the shadow pass so that we can voxelize and capture that 3D data. That's pretty much it. That's all we need to do there. I think there was 1 or 2 other things you might want to put in here that I'm not sure what they are. One is the option to make sure the shadow pass always renders even when we're not sampled. I've got a workaround in this tutorial right now, but there is something to do to make it do that automatically. Because if you don't sample the shadow map, the shadow pass won't run. So we're sampling it because I don't remember what the option is. So if you find that out, you can replace that code. And the other thing, I don't remember, but if I remember, we'll cover it. back at the README, we are doing the voxelizing in 2 places, either in GBuffer's train or shadow vertex shader, which is using its own GLSL to do it, so that you can more easily see what that is. So if we look at GBuffer's train vertex shader, here's where the code is. We're using version 430 because we want to use the 3D images, and those just aren't available, I don't think, on the earlier versions. Here is the 3D image that we're writing out to. Here's just other stuff we need. Then we've got some stuff we're passing out that isn't really necessary, but it is for some of the ways. Now by default, this is our standard shader, would just be that, and writing out the vertex transform. The rest of this that does the voxelizing, I'll show you how I'm doing it in the shadow pass here to make it a little bit more simpler. It's doing the same thing, it just does what it does, and then we're doing voxelizing if we're voxelizing here versus in the other spot. So to see what this code is on its own, let's look at it. First thing we're doing is we're going to get our positions figured out. We want to get to foot position, because this is our position relative to the camera. If you're not familiar with the positions and the position transforms yet, you should do some of the other tutorials. But basically we've got a 3D texture. It is basically a cube that's going to hold the data around us. So we're going to put ourselves in the center, and we're going to put the stuff in the world around us. So the stuff that was red was outside of this cube. And the way we're going to organize this cube is we're going to, in the position chart, if this is us, a little stick figure, foot position is just the way things are around us. It's not the way we're looking. That's like the camera positions and all that. But the foot position is aligned so that north is north and south is south, and it's just centered around us. So we're going to use that as the 3D cube where we store data. So we can just kind of like say, okay, there's the cube. This is our 3D space. So the foot position is basically it, except in foot position we are at 0, but the 3D texture, just like all other textures, ranges from 0 to 1 on each axis. So instead of us being at 0, we want to offset it. So we're going to take kind of like a radius, like half the distance. So if this is 32 blocks across, we need to take half of that, which is 16. And instead of having this be negative 16 and this be positive 16, we're going to shift it over those 16, that radius, so that they'll be stored in that 0 to 1 range. So we're going to take that foot position, and then here's where we get into our voxel map position. We've got the area, which is how big it is, and the radius is just half, like I just said. We center it with the mid-block. Mid-block is something that Iris gives us. I'll draw a picture about this too. It's a thing that makes voxelizing difficult is if this is our Minecraft world and these are all blocks that are next to each other. Let's say this is in like area 1, area 2, area 3. The problem with this is that in our world space, this is 0, this is 1, this is 2 feet from origin, this is 3 feet from origin, or meters, I guess, because each block is a meter. So at this corner here, it's both in block 1 and in block 2. So if you just try to voxelize based on where that is, it kind of flicker back and forth between them. These corners would all flicker between these 4 and the 4 above them. So what mid-block does is it tells us how far a vertex is from the center. So if here's a block, here's a vertex, here's a vertex, here's the center, it tells us how to get to the center of the block. Because if we, instead of writing at the corners, write at the center of the block, we won't get flickering from everything fighting over which positions they're in. So here we take our foot position, we add the at mid block, which over 64 brings it back into a block space, and we add the fractional amount of the camera position so that we align things that as the camera is moving, instead of them sliding around, they stay in that block gridded out voxel position. if we get rid of this, we'll see this get messy. Yeah, see, like, it's horrible without that. So you need that. Every bit of code in here is needed. But I want you to understand what it's doing so that you can do more with it, and do different things. So our voxel position is not a vec3, instead of it's an ivec3, which instead of being a float or a decimal is integers or solid numbers, and that is pretty much, this is which voxel we are in. So that's our block relative position plus the voxel radius, which, like I said, we're offsetting it to be in a 0 to 1 range. Well, to be centered around the center, that's what I mean. It's not 0 to 1 as this image here. But we've got this, the way we've got this declared, it's both as this way we can write it, or that we can read it as a 3D image as a sampler. Like, there's two different ways to do it. This way is like the layout, and this other name is for using texture 3D, which is like texture 2D. I think we just use it this way, but you can do either. So now that we know which voxel, which part in this 3D texture to write to, because the 3D texture is, again, just a cube around us. And if it's 32 blocks, then that means it's 32 in each direction. So once we've taken, here's us again, and let's say here's the ground, and we've got a certain block right here. If that block is 5 blocks to our right, then it's going to render it at 5 blocks to our right, which, if this is 32, then being the center is 16 points up. So if we have an X, a Y, and a Z, the Y is how far up it is, so it would be equal to us. Let's say that the camera's at our feet, so that would remain 0. The X position is that it is, actually the Y isn't 0, in the middle is actually halfway up would be 16. And then to the right, it is at the center, which is 16, but then plus another 6, so that would be 22. And then how far north is it? It's just right in the middle, so that would be 16. So that's what we're doing with that code so far, is we're taking where it is compared to us and deciding where it is in this texture, which is either 0 to 32 if we read it in the one way, or it's 0 to 1 if we read it the other way. But we're making this cube. That's our voxelizing data, is we're just putting stuff in that 3D texture. So now we're going to write our data. What we're going to do is we're going to check a few things. We want to only write for one vertex on each face, because each cube has, well, like 6 faces, and each one of those has 4 vertexes, but we don't want to write every vertex. It's kind of redundant. So we're just going to say that if this ID mod 4 equals 0, which means it's only 1 out of every 4, and then we're going to check if it's within the right range. And we can do that by just clamping, because if we clamp a number between 0 and the voxel area, then if it's outside of that range, 0 to voxel area, it won't equal what it already was, but if it is in that range, it will be the same. So that's a way to check that. So then now we're saying, yes, we're going to voxelize. Here's where our options in our menu does different things, where we're choosing the color average. What we do is we just sample our texture like we normally would. This could be texture or G texture. This is where we normally would get it in the fragment shader. And here, this log 2 is we're just sampling the entire size of the texture, and it's map that gives us the average color. And here we're applying the leaf color. If we do the position, our voxel data is just doing the position in a way that we can visualize it. If we take just pixel of one color, here you see we're doing texture LOD, just at the text chord, at just the regular LOD level. If we wanted to do lighting like flood fill, you could go off of this, where we're taking the at midblock.w. The at midblock, which takes us from the outsides of the block into the center. The W component, since it isn't used, they're just 3D, gives us how bright that light is. So we can use this for lighting. So that's how we capture the light data, and then we would propagate it outwards in like a compute shader. And then here for the block ID stuff, where we checked about the grass, we were checking if our entity ID, which would be in our block properties file, we just tag grass as 10,000 and dirt is something else. If it's 10,000, we're making it green. If it's dirt, we're making it brown. That's all there is to it. And then here's where, when we first start, it draws blue around the character. And then what we do is we're going to, the format that we have for our image, we had to set things for it here, is we're using a 32-bit unsigned integer. It's an unsigned integer. And the reason we're doing that is that let us use atomics, which is a special set of things, where instead of just writing a value to a pixel blindly and then the blocks are fighting over it, we can do different things with it. If you remember, I think we've talked about before about parallelism, that if this is our GPU and it's got a bunch of pixels that it wants to draw, or in this case a bunch of voxels that it wants to write, it handles a bunch of them at once. And you never know which one's going to finish. So if we get in a situation where more than one thing is trying to write to the same pixel, or more than one thing is trying to write to the same block, you get what they call a race condition, because you don't know which one's going to write first, and which one's going to write second, and which one's going to write third. So you get flickering, as it's like Z fighting. They're kind of fighting over which one has that spot. Even though we did that mid block, there's still other ways that things are going to be fighting over positions. Like for example, if we've got something with more than just a block of faces inside of the block, like let's say we've got a fence post that has more blocks because it's got more faces. So they're all trying to write in that voxel at the same time. So to get around a race condition, we can say, okay, instead of just letting them all write with the same sort of priority, we can say that we're going to compare them to each other live. And the way it does that is something called atomics, which lets you do things like take the maximum value of what was already in that spot and what you're trying to write, or do things like that. So instead of them fighting over who gets to write in the square, they all say they want to write in that square, and the atomics does logic on them and decides which one actually stays in the square. And the 32-bit, like this format of red integer, 32-bit unsigned int, that means that we have a 32 bits of data we can put in there. And one of these, I'm trying to remember what these are, it's whether or not it clears and whether or not it's relative. It's not relative, so we are having it clear every frame. So with that we can do atomics. If we look back over here, since the atomics are an unsigned integer, an integer that's 32 bits, we need to make sure that our voxel data that we're saving is saved as 32 bits. Since it's 32 bits, you can do all kinds of stuff with it. If you wanted to, you can have, because here's our 32 bits. When we were doing normal stuff with like red, green, blue, and alpha, each of those is 8 bits by default. So you could have 8 bits for 4 different things, like a red, green, blue, and alpha. And that's what we're doing just for simplicity. But if you're voxelizing on your own and trying to do other things with that data, you can save other stuff in there. You've got 32 different bits. So you can have 32 bits of information, which means you can have one thing just be a true false of, is this fire? You can have a true false of, is this wet? If you wanted to have other numbers crammed in here, you could do something like an 8-bit that gives you 0 to 255. Or if you wanted just to use 2 bits, that would let you count 4 different things. This would let you count 8 different things. This would let you count 16 different things. So you could have one value, like let's say you wanted red to only take 16 different values. You could have it just be 4 bits instead of 8 bits. And you can kind of tally these up how you want, to use them how you want. That sort of bit stuff is outside of the scope of this first one. we're just trying to put stuff in there. So what we do is we use this built-in OpenGL function, which packs 4 8-bit values into an integer. So we're taking our voxel data, which depending on what we're visualizing is just our color or whatever, and we're taking that red, green, blue alpha, cramming it into an integer value, and then we're using image atomic max, which is one of the functions that lets us write data into with atomics. Some of the other things you could do is image store just throws it in there, but we're doing this so that if multiple things are trying to write to it from like a fence post, it's going to take the highest value of them and use that one, so they don't flicker fighting over each other. So here we're writing to our C image at the voxel position, and we're writing that integer value, which is the packed data that we chose depending on our option. And when we're writing to these, we use an IVEC instead of a VEC3 when we're writing with atomics, because it's writing to the pixels, and the pixels are definite instead of being a gradient between each other. So that's how we're saving the data. Let's look at how we're using the data. So again, we're using version 430 because some of this stuff needs that. It needs newer iris. All of this is your standard stuff here. And then to show where our voxel range is in the shader, that red on the edge, and we can make this smaller to make that more apparent. That's what we're doing with that right there. And this flicker here is, like I said, if we're doing the voxelizing in the shadow, right now it's voxelizing everything. So this entity of the bed is fighting with the wall on which thing is in that spot, because the wall has that midchord thing that lets us suck it into the middle, but the bed as an entity, I don't think it does. So they're fighting over that spot, which is why you would, let's see, let's switch this over. If we voxelize just in gbuffers terrain, then they're not fighting because we're not voxelizing the entities. So there's not two things in the same spot. All right, so let's look at the next part. Here we are just redefining this stuff because we don't have a main settings file. And here we're showing two different ways to get the voxel position. This is just if you want to learn. In the fragment shader, we can just pass this data because in the vertex shader, we are we have it as an out, like a varying. In and out in these is the same as varying in the ones we were doing before in the version 120. In version 430, instead of doing varying for both the vertex shader and fragment shader, you say that you're sending it out in the vertex and that you're taking it in the fragment. Well, it's the same thing. Here where we were calculating that block-centered relative position, we're passing that forward optionally in our gbuffers vertex shader, or we can reconstruct it using the foot position and the normal's face in the world position. And the reason this is here is because you're not always going to have that data, but for any random pixel and stuff, you can have this data. You can calculate the foot position for a pixel. In this case, we were passing it forward, but you can recalculate it from where a pixel is on the screen using the space conversion chart. And you can also have this data. Very commonly, you'll have the normals of your face. And you can put them in world position. So then we're going just a tenth of the block in, and that's re-accomplishing the effect that we were getting with the midchord, but doing it without having midchord, because there's situations where you're not going to have that while voxelizing or using voxelized data. So that option is there just to show you that you could do it two different ways, and it looks the same, at least for the blocks I tested. And here again, we're checking if we're in voxel range now before using any of the voxel data. We get our vec4 bytes, we unpack reading from the texture, the 3D texture, and we're reading at csampler1. What this is that is in our shader.properties, where we declared this cimage1. We also gave it the name csampler1. we can do an image load from image 1, or we can do texture 3D from this. It looks like in this case we're choosing to read it from as texture 3D. So if we do that, we're not going to use an IVEC, we're going to use just a vec3 that is in a 0 to 1 range. So we take our voxel position. Oops, I got ahead of myself. Take our voxel position, and we're doing that over the voxel area to get a 0 to 1 range, since we're reading as a texture 3D. So it's 0 to 1 to be from one end to the other. And then we're setting our color to those bytes, and that's our default thing. And then this is just going over the different things we did with it. If we did block IDs for the grass, that's shown here. If we were debugging our alignment, that's shown here. And this code right here is literally just to make the shadow pass run, because like I said, I don't remember what that thing is that we would put in the shader.properties. Someone might have just told me on Discord. I just want to get the video done, and you can figure that out and put that in. But that's the basics of voxelizing. Is you normally want to do it in the shadow pass, because when we run the world and it renders, if here's us and we're looking in this direction, Iris will only draw stuff that's here. It's not going to draw a tree that's behind you or a house that's behind you, because it wants to say performance. But the shadow map draws just focused around you, like a big area. And even though it also does culling that hides things behind you, when we set culling to false or reverse culling to true, it's going to take that distance around you that we set and still draw things there, so that we can voxelize all around us. And I did not show that. That is actually in, it says it in the README, it's in the composite. You have to set this number in a composite shader or the final shader. So we just put it here. And I'm not sure if we could set it to a define like this. So we just did if this, if that, set it to the numbers. But that's the basics of voxelizing. That's all we're doing, is we're figuring out where each block is in the world compared to us, based on where it is compared to us in the shadow map, or the gbuffer strain, and then we're going to take that data, whatever data we want about it. Like if we wanted to do lighting effects, we would take our light emission here, and we'd probably want more range than that. And this tells us where lights are. And then we'd probably also want their colors, and we showed how to get the color. And then we would do something with that data. So the voxelizing just gives us the data, and then we've got to decide what we want to do with it. So if you want to do flood filled colored lighting, you would do that with the data. If you want to do special effects, like where I've got like have people leave a path behind them or other stuff, or like just whatever you want to do, you can do it with that data. So most of the code is just like we see here. If we do it in our shadow pass, it can all be squeezed just in this one file. And pretty much all we do is we get the position of where it is in the voxel map, and then for one vertex at least of each face, we pick what data we want to write. Like if we wanted the color, if we want whatever we want, we convert it into a 32-bit format so that we can do atomics, and then we just write it to that voxel. And then the fragment shader, same thing. We need to figure out where we are in the voxel map. And the way we did that was taking our foot position, because that's us in the world space. We went back into the lock using the normals. We added that fraction of camera position to keep it from being all weird. And then if we're in the range, we load from that 3D image we made at the right position. Then we've got that data, and then we could do whatever we want with it. And that's voxelizing, which is your gateway to doing all kinds of 3D effects in Minecraft, and to fit a really big square, or fit a really big circle. You're fitting a circle in a square peg, and you can make the circle as big as you want and do as many fancy, crazy effects as you want to, because now you've got data about the whole world in whatever range you want. Did what you want with. So that's it. If you guys want to see something about like specific things to do with this, you can leave me comments here or on Discord or Patreon, and we'll figure out, and I'll do a poll at some point about what to do next. I might do one with flood fill lighting. Anything other than colored flood fill lighting is probably too complicated to do in a quick video, and is the kind of thing that you, like from this point, you've got to figure out what you want to do, and then you've got to figure out how to do it. But this part itself was extremely frustrating to get going at first, and I wanted to save you that frustration, because just little things like this can haunt you for a long time. But I hope you all had fun, and I'll talk to you soon.